right, this is day 5 of our Unit 4 on polynomials, and this will be our last lesson of this unit. Next class period after this is the review, and then we will have the test on the unit. So today we're going to be looking at graphs of polynomials. So first of all, I wanted to remind you that transformations can work with any type of graph, and that includes polynomials. Now, we don't typically graph polynomials in the same way that we graph parabolas and absolute values and lines, in that we oftentimes don't sketch them as often because they're more complicated, and more typically we use technology to help us get the shapes of these things correct. But we could, if we know what the function looks like, we could think about what transformations of that function might look like. And again, this would the actual shape itself of the graph will depend on which polynomial function it is, but if we know the shape of the polynomial, we can transform it. So here's our function f of x right here. This happens to be a cubic polynomial function. We could transform it by either adding 4 as a constant at the end of the function, or we could add 4 to the x value in the function, and that will transform it in 2 different ways. And you might remember, hopefully, from other function types, that if we add 4 as a constant at the end, here, this is a vertical translation. It will move it either up or down. In this case, it's going to go up 4. And if it is with the x, that translation is happening in the x direction, so that's left to right. In this case, since it's an x plus 4, it will move to the left 4. So put the arrow there, left 4. So if we're moving f of x down 4 spaces, what I like to look at is those intercepts. So right here would be our intercept, but we're going to move that up 1, 2, 3, 4 units. And here would be our intercept, but we're going to move that up 1, 2, 3, 4. And the last one would be here, but we're going to move that up 1, 2, 3, 4. So these 3 points will be on our function. And you could look at a lot of other points to sort of get the shape. Let's look at the y-intercept for fun. Here it is at positive 2, and we could move that up 4, and it will now be at 6. Sometimes people like to look at the mins and maxes. The relative max is just a little above that, so it'll be like here, and the min is about 2.5 below those 2 intercepts. So over here would be approximately here-ish. And if we have all of those points, I mean, you can kind of decide how many points you think you need to get the shape right. We're just trying to do a sketch. I think usually 5 points or so gives me a good idea of where the function goes. And here it is. It's not perfect, but it'll do. It's a good sketch. If we're translating it to the left or right, I use those same intercepts again. -2, if we're shifting it back 4, would be at -6. +1, if I shift it back 4, will be at, let's see, if it was here, it'll go 1, 2, 3, 4 at -3. And the last intercept, it is currently at 4. If we shift it back 4, it will be at 0. And I'm going to do that same thing with the y-intercept. Here it is at +2 right now. If we shift it back 1, 2, 3, 4, it will be here. And again, the max is a little higher than that, and the min is down here at -2.5 about. So that kind of gives me a guideline for what that shape looks like. Sometimes when you're talking about shifting these left and right, it's hard to see exactly what the translation was, because when you look at them, you're like, well, it looks the same. And they kind of look the same. You just have to notice that the intercepts are different. Another transformation that we can do with functions is to stretch them. So same function f of x, we're going to look at what happens when we multiply f of x by a number, and I'm going to change it to 3 because 4 doesn't quite fit on our coordinate plane very well in this case. So we talked about, quite a few days ago, we talked about how if we stretch a function out, it doesn't change the intercepts, or if we stretch a polynomial function out, it doesn't change the intercepts. So if we took this same function, we multiplied it by 2, that just means it would be twice as stretched out. Or if we multiplied it by half, it would be half as stretched, like this. So 3 times f of x, and it's going to have exactly the same intercepts at -2, 1, and 4. It's not going to change those intercepts. It's just going to stretch that function out. So it will be 3 times as high. Well, right now it's about 2.5 high. So if we times that by 3, it'll be about 7.5 high. So it's quite high. The intercept right now, the y-intercept, is at 2. So if we times that by 3, let me erase some of these other lines so we don't get confused by them. The y-intercept right now is at 2. If we times that by 3, it's going to be up at 6. That kind of gives us an idea of how tall this thing is going to be. And then we, of course, also will have it dip down, and right now it's dipping down about 2.5. So it's going to be down around 7.5 if we times that by 3. So something like this, much more stretched out. If we times by -1, it's also considered a stretch. The negative stretch, though, reflects it. So again, it's going to have the same intercepts, -2, 1, and 4. But in this case, instead of starting by going up, we're going to flip this over and it's going to go down. So that y-intercept will be -2 now. And on the other side, instead of dipping down and heading up to infinity, we're going to flip that over. It's going to go up and down, like that. So that's what our function looks like when it's reflected. And reflection in function notation looks like timesing the function by -1. Okay, so now we're going to look at some pictures and try to decide in function notation what we might write it as. So this first one, if we're looking at this, hopefully you maybe notice that it looks like it has been shifted up quite a bit. You can look at the intercepts to see if that helps you figure out how high up it went. At -9, it's right here now. At -1, it's here now. And at 4, it's here. It can be kind of tricky to figure out what happens to these functions because of their curvaceous nature. You just kind of have to play with it and think about it, and if you decide what you think happened to it, test other points and see if that worked. If it really is doing that, you could look at the y-intercept right here. It's a little bit, it's below 0, but not quite as far down as -1. And here it's between 3 and 4. And whatever you need to look at to sort of decide how it moved. But what happened is this thing was shifted, this function was shifted up 4 units. So it was down here, now it's up here. And if we want to show in function notation that something moved up 4, it's that function plus whatever the constant it shifted up by, which in this case was 4. If it had shifted down, we would have written f of x minus 4. So here's one. original function is f of x. I want to know what did we do to f of x in order to turn it into this graph b? Well, I think this one is a little easier to see what happened. It looks like it was reaching a peak around 3, and now that peak is way up at 9. But it didn't shift up because we have the exact same intercepts. In this case, it's stretched. This is a stretch of, well, the 3 is now up at 9. This is a stretch of 3. So it's 3 times f of x. Another graph C, how did it change from f of x? I think this one is difficult to see. If you're not sure what's going on, I would check the peaks and see if they're at the same height, and in this case they are. And then the second thing I might look at is the intercepts. Here it's at -9, -1, and 4. And here it's at -7, +1, and 6. It looks like each of these intercepts shifted towards the right by 2 units. So it went 2 to the right. And how we can write that in function notation is f of x minus 2. Remember those horizontal ones, they're always the opposite sign of what we think, for the same reason that if we're solving a factor, we switch the sign, really. All right, D, f of x is this function that we've been looking at, and now we have this function d that looks quite a bit different than f of x. It has, though, if you look, the exact same intercepts, -9, -1, and +4. So this has to be a stretch. And in this case, you might notice the behavior on the ends. This one was down and then up. This one's first high and it goes down low. It's just flipped over. Here it went up 3. Here it's going down 3. A little dip here and a little bump here. This is negative f of x. It's reflected. Last one is also reflected. I can tell that because of its end behavior. It's the opposite end behavior. And it has those same intercepts, so I know it's just a stretch. It's definitely negative because of the reflection, but it's not nearly as high and low now. This was up at 3 as its relative maximum height, and now it's more like -1.5. And here it was a little more than -1 for its minimum. And now it's not quite -1. It's more like about a half. So hopefully you can see from these numbers that this is half of f of x, and it's reflected, so -1/2 f of x. Okay, so we can transform polynomial functions. It's also useful to be able to sketch them without use of a graphing calculator. You could always use a graphing calculator to help you get the idea, but the problem with graphing polynomials on graphing calculators is that unless you're really good at adjusting the window, they can be difficult to get a good picture of. So we're going to do some graph sketches of polynomials just using the end behavior and the factors. If our polynomial is in factored form, it's going to be just ready to go. We don't need to do any extra work to graph that. If it's in standard form, we will factor it first in order to put it in intercept form. So our first one will be already in intercept form here. It's g of x equals x plus 3 times x minus 1 times x minus 4. So the first place we want to start with graphing these functions or making sketches of these functions is I want to know the real zeros. Well, each of these roots corresponds with a 0 of the function. The factor x plus 3 corresponds with the 0, -3. The factor x minus 1 corresponds with the 0, 1. and the factor x minus 4 corresponds with the 0, 4. Essentially, we're setting each of those factors equal to 0 and figuring out which value would make that factor 0, which is why they're called the zeros. Each of those zeros corresponds with an x-intercept. So -3, 0, 1, 0, and 4, 0 are our x-intercepts. -3, 1, and 4. The end behavior of the function can help us know whether the function looks like this, or like, whoops, sorry, that's the same, or like this, or some other behavior. We sort of need to know what's happening on the two sides of the function. So we'll think about the end behavior of the function. In this case, so our question is it even or odd? And is the leading coefficient positive or negative? Well, in this case, the degree of my polynomial has 3 factors. This is going to be a degree 3 polynomial, which is odd. And the leading coefficient, well, we have a 1x and a 1x and a 1x, so the leading coefficient is just 1, so that is a positive number. Well, odd positive polynomial behavior, the odd tells me that the two ends are different, one's up and one's down. Positive tells me overall it starts low and goes high. So our ends are going to be on the left, down, on the right, up. On the left will be down, on the right will be up. And that end behavior sort of tells me, it's got to go through this intercept, and it has to go through this intercept, and somehow these parts have to connect because it's continuous, and the only other place it's going to cross is at 1, so it's got to kind of go like this. Now, it's good when you're doing these sketches to also note the y-intercept, which in this case looks like it's right here. Now you'll notice there's not a scale on that axis because the, well, when we're graphing polynomials, we often don't have a scale on the y-axis, or the scale is just not the same as the x-axis. And I left the scale off these completely so that you could just note where the y-intercept is. The y-intercept of this function, well, remember the y-intercept happens when x equals 0. So if we put 0 into our function, g of 0, it's 0 plus 3. 0 minus 1, and 0 minus 4 all multiplied together. That's really just the same as saying what's 3 times -1 times -4, in which case that would be 12. So our y-intercept is 0, 12, and on the graph I'll note that that is a value of 12. And now I kind of know what the scale is. Again, this is just a rough sketch of the polynomial. Here's another one, f of x equals negative quantity x minus 4 squared times x plus 5. So we start by listing the zeros of the function. For the factor x minus 4, the 0 is positive 4. And for the factor x plus 5, the 0 is negative 5. We do have a multiplicity here, which will affect the behavior of our graph. So we have 4 and negative 5. And put a little note to myself that I have a multiplicity of 2 here so that in a minute I can use that. The end behavior of the function, I need to think about, is this function an odd function or an even function? Well, negative x minus 4 squared times x plus 5. Well, it's got 2 factors of x minus 4 and it has a 1 factor of x plus 5. Well, altogether that's 3 factors, so this is degree 3, which is odd, an odd power function. And in this case it's negative because it has this negative coefficient, so my leading coefficient would be, or not my leading coefficient, but my leading term would be negative x to the third. The leading coefficient is negative 1. So this is odd negative. Odd negative functions, or odd negative polynomial functions have ends like this, where the right is going down. Overall, the function, if you look at it from left to right, is decreasing. So over here it's down, and on the left it's up high. Well, the multiplicity here at 4 tells me that the function is not going to go across the x-axis, but it's going to touch it and turn around. It's the tangent point, remember? And then it's got to go up through this other one and connect there. So it looks something like this. And if we find the y-intercept, that's putting 0 in for x. We want to know what the y-intercept is. So it's negative 0 minus 4 squared, 0 plus 5. And if we calculate that, it's like negative 4 squared would be 16 times the 5 is that's a positive 80. And then we also have this negative in front, which makes it negative 80. And you could just calculate it with your calculator if you like. So down here, this intercept would be negative 80. One more. Now this one is in standard form now. It is not in intercept form. And all that means is that we should try to factor it to put it into intercept form. This has 4 terms. We're going to try the method factor by grouping. So for factor by grouping, we think about the first 2 terms and what they have in common. In this case, they have in common 4x squared. And if we factor out of 4x squared, that leaves behind an x plus 5. And we look at our second group here and we think about what do they have in common, and what they have in common is a negative 9. If we factor out the negative 9, that leaves us with an x plus 5. Now again, this is positive right here and not negative because we factored that negative out. Both of those negatives are with the negative 9. Now you might notice that we have an x plus 5 in each. Whoops, I erased my x plus 5. We have an x plus 5 in each of those terms, and we can factor that to the front. And what that leaves us with is, in this first spot, 4x squared and a minus 9. X plus 5 can't be factored anymore. It's just a little linear factor, but 4x squared minus 9 can be factored just a little bit more. It has a lot of perfect squares. 4 is a perfect square, 9 is a perfect square, so we can factor it as 2x plus 3 and minus 3. So there's our function in intercept form. So the real zeros of this function are going to be negative 5, negative 3 halves, and positive 3 halves. Remember that 3 halves is about the same as 1.5. So on our graph, we've got an intercept here, and here halfway between 1 and 2, and here halfway between the 1 and 2, both positive and negative. End behavior of this function comes from the leading term because it's in standard form. So this is an odd power, and it has a positive leading coefficient. So it would have behavior where it's up high on the right, down low on the left. So starting low, going high. So over here, and maybe over here. And there's no multiplicities or anything, so it's just got to simply go through those and then connect in between. For the y-intercept, again, we're in standard form, so that's fairly easy. The y-intercept is the constant in the function, so it's negative 45. It's nice to find the y-intercept when it is in standard form. And that really is the same thing you would get if you plugged 0 in, because you would end up with 0 to the third, which is 0, and 0 squared, which is 0, and then 9 times 0, which is 0. So really the only thing left, if you look at it that way, is negative 45 as well. So any way you look at it, the y-intercept is negative 45. Okay, this one was for you to try in class. I had them do it and then check their work. I want to just go over the factoring of this with you really quick, since factor by grouping can be difficult to learn. So if we're factoring this by grouping, I would factor out an x squared. That's what those first 2 terms have in common. That leaves an x plus 6. In the second group, I would factor out a negative 4. And from the first term that would leave an x, and from this second term that would leave a plus 6, so that if I multiplied those two out it would be a negative 24. And so we can factor the x plus 6 to the beginning because it's in both of the terms, and that leaves an x squared minus 4. And we can factor that x squared minus 4 just a little bit more. X squared minus 4 is the same as x plus 2 and x minus 2. So the real zeros of this function are 2, that comes from this factor, negative 2, that came from this factor, and negative 6 came from this factor. And you can see the graph there. Okay, we're almost done. The fundamental theorem of algebra we've talked about before, and it guarantees that the number of roots of a polynomial function is the same as the degree of the function. And that guarantee is in the complex number system. So that includes both the real roots, like things like 5 and negative 2 and 0, and it also might include things with imaginary parts, and we've solved more than a few equations that have i's in them. If we don't include the possibility of imaginary ones, the fundamental theorem of algebra doesn't work. We have to include complex numbers in that. So most of the polynomials we've been looking at least with graphing, have real roots, but they're not always real. Sometimes they do have these roots that have an imaginary part. The real roots you can see on the graph. They are the x-intercepts. The non-real roots, sometimes there's evidence of them, but you can't find their value on a graph. We'll talk a lot more about the imaginary roots later in the next unit, but I think it's useful to remember where they come from. Non-real roots we generally find when we use the quadratic formula, and it's when we have a square root of a negative number as part of our quadratic formula that we're working out. Because of that, they always come in pairs. If you use the quadratic formula, you'll have this plus or minus symbol as part of it. And so you would have both of those roots, one with the plus and one with the minus. They come in pairs. So anytime we have non-real roots, they do come in pairs, not ever as singles. So I want to just think about cubic polynomials for a minute and what sorts of possibilities we might have. We've graphed quite a few that have this sort of generic cubic shape. And because it's degree 3, I know that there are 3 total complex roots. And if I look at the graph of this function, I can see evidence of 3 real roots. And what that means is that for this particular cubic function, I know that it has no non-real roots, because the total number of roots it has is 3, and I can see on the graph that all 3 of them are real roots. Well, a cubic function could also look like this. It's a very similar shape. Maybe you could think of it as being transformed up 4. Again, it's a degree 3 polynomial, so I know it has 3 total complex roots, but when I look at the graph, I can only see evidence of 1 real root. And what that means is that there must be 2 roots that are non-real, that have an imaginary part. If you looked at a graph of a function like x to the third plus 8, it might look similar to this, where it has only 1 real root shown, but it does have those other 2 roots. They're just an imaginary part. Another way a cubic function might look is maybe like this, where it just touches the x-axis right here. Again, it's a degree 3, so I know it has 3 total complex roots. But if I look at the graph, I see 1 here, and I only see 1 here. except you need to remember that this root has a multiplicity of 2. That behavior of just touching and turning around on the x-axis indicates that it has a multiplicity of 2. So there really is evidence of 3 real roots there. And so this type of function, in fact, has 0 non-real roots. Another type of cubic function you might see is a terrace like this. And again, at first glance, it might appear like you can only see evidence of 1 real root. But if we remember that this behavior is telling me that it has to have at least a multiplicity of 3 because it's a terrace, I can see evidence of those 3 real roots, and it does not have any non-real. Because it has a total of 3, so if I can see evidence of all 3 being real, that means it does not have any non-real. I want to think also for just a minute about quartic polynomials. I'll show you some of those shapes. Quartics are degree 4, so the 2 ends, it's even, the 2 ends have to be the same. So I'm going to draw these as kind of W-ish shapes. So the first possibility might be this. The function is a degree 4 function, so I know it has 4 total complex roots. And if I look at this particular graph, I see evidence of 4 real roots. Well, that must mean that in this case, it does not have any non-real roots. It has 4 total. I can see all 4 are real. Another shape might be this. Again, it's degree 4. I know it has 4 total complex roots. Fundamental theorem of algebra guarantees me that. But when I look at the x-axis along here, I see no evidence of a real root. There are no real roots. Real roots show up on the x-axis as intercepts. So that must mean that for this particular function, it has 4 non-real roots that have an imaginary part. It's good that it's 4 because remember these non-real roots come in pairs, so it should always be an even number. Another way that a quartic polynomial might look is like this. Well, in this case, it's degree 4. I know it has 4 total complex roots. And if I look at the graph, I see evidence of 2 real roots. Well, that must mean, since I only see 2 real roots, that it has 2 that are non-real. Another way it might look would be with, let's see, let's do touch. Oh, I missed. And that's when you know you need to calibrate your smartboard. Here we go. It's a quartic function. I know it has 4 total complex roots. I see 1 here, but it has a multiplicity of at least 2. And I see 2 more here. So altogether, I can see 4 real roots. So it must have 0 non-real. And the possibilities go on and on. What if we had a little terrace here and a dip down and up? It's not a very good terrace, but it's a terrace, I promise. Well, in that case, if I remember the multiplicity 3 here at this terrace, I can see 1, 2, 3, 4 real roots. Sorry, 3 are here and 1 more here. So this would have 0 non-real. And let's think of another scenario. Oh, here would be a fun one. If it squiggles like this, touches and turns around. I know it has 4 complex roots because it's degree 4. Of those complex roots, I have this one I can see right here, but I remember that that behavior tells me that it's a multiplicity of 2. So I have 2 real roots, and the non-real roots would be a total of 2 of those. Anyway, there's other possibilities with quartic. This is just some of the possibilities. So let's look at that in practice. So oftentimes we might see a polynomial and want to know how many roots it has that are real and how many are non-real. The degree always tells you the total number of complex roots. In this case, this function is a degree 3 polynomial. It has 3 complex roots. When I look at the graph, I see evidence of 1 real root, and therefore it must have 2 that are non-real. I look at this function, this next one, and it is a degree 6 polynomial. So I know that it must have 3 total complex, oh my gosh, woo! It's a degree 6 polynomial. I know it has 6 total complex roots because it's degree 6. I look at the graph for evidence of real roots. I see 1, 2, 3 because that's multiplicity 3. Here's another one that has multiplicity of 2 because it's a tangent one, and one more. So if I add that up, I've got 3 plus 2 plus 1. I can see a total of 6 real roots. So this has 0 non-real roots. The last one is a degree 8 polynomial. So I know it has 8 total complex roots. If I count up how many of those are real, I've got a little terrace point here. So that has a multiplicity of 3. I've got a little tangent point here that has multiplicity of 2. And I have one more root over here. Well, that's a grand total of 6. And if it has 8 total, that must mean that there are 2 non-real roots. And that is it for today. Next time we'll be reviewing for the test will be, this has a quick little list of topics that are included on your test. So much of what we've been doing this unit is just related to the idea that the x-intercepts of a function are related to the zeros of the function, which is related to the factors of the function. All those things are so closely related, and next time we'll be reviewing and have a test on that.